This week we're going to talk about motion planning, and we're actually going to be talking about motion planning for quite a while, so I'm labeling this as part one. And the first part of this is graph search for path planning. So just to recap real quick, last time, well, not quite last week, but last time, we talked about computing odometry information based on wheel encoder information. So you may recall that odometry information basically means the position and orientation of the robot, and wheel encoder information is the distance that each wheel has traveled. So by only knowing the distance that the left and right wheels have traveled, we can actually compute the robot's position and orientation as it moves. We also talked about how to move the robot at a specific velocity based on how we want to spin each wheel. So we know that if we want to move the robot at like maybe half a meter per second, we can compute how fast do we have to spin each individual wheel to actually achieve that velocity. And essentially what we were talking about is called local control or local planning. And it's a sequence of actions, so our actions being motion states or motor commands, to move a robot a small distance. So by small distance, I mean generally in terms of millimeters or centimeters. And as you drive the robot, you have lots of sensing information that is being sent back to the robot about how it's moving, and we can check, is this moving how we expect it to move? If so, then we can not change anything. If it's not moving how we expect it to, we can alter how fast we're spinning the wheels to achieve the speed that we want. And in class, what we did was teleoperation. So you said, okay, if I press a button, the robot will drive like 1 meter forward. If I press another button, it will like turn 90 degrees. Essentially what that was a basic local control loop. So local control for like real world robot applications, it gets very involved. But essentially what you were doing last week in class was a very basic local control loop. But today we're going to start talking about motion planning. And so at a very high level, motion planning just means finding a sequence of motions that moves a robot from some initial state to some goal state. So I put two examples here. On the right-hand side, you just see like a 2D plane, and we have some start position Q0 in the bottom right, and then we have the circle up here labeled G as the goal. And we've got a couple obstacles, and we have just this little curve to move a robot from the start to the goal. So that that works for mobile robots, but we also have to consider robot arms. So motion planning is a really big deal for robot arms, and over here on the left, we've got some start position, and then we've got some goal position, and they're on different sides of the box, and we want to move this arm from one side of the box to the other side of the box. That is also a motion planning problem. And motion planning combines local planning with global planning. So again, what we have been talking about the last week or so was local planning, so moving small distances. Global planning is more about moving long distance. So it's like, if I want to move from one room in Woodward to another room in Woodward, what is my path to get there? Like if I want to go from the robotics lab on one side of Woodward all the way down to my office, which is, quite a ways away, what's the overall path I have to take to get there? And essentially, global planning is just called path planning, whereas local planning is low-level control. You can also call it obstacle avoidance. So these two things are different. So with path planning, we're mostly just concerned with geometric information. So we might have some space here. We want the robot to move from point A to point D, and we have these little intermediate points B and C. And we say, oh, okay, well, to move from A to D, I just first need to move to B, and then to C, and then to D. But that's only like positions, right? That doesn't really tell us how to actually drive the robot. So control is focused with the driving part, the actual motion information. So with control, we would ask the question, well, how do we move from A to B in 1 second? And that might entail something like drive for half a meter per second in some direction, theta, and really what that means is, okay, we're going to have to apply some acceleration to our robot. And in order to apply some acceleration to our robot, we're going to have to send some motor commands to spin the robot's wheels at the correct speed. So what we're going to be talking about here is on the left, the geometric information. There are lots of interesting things to talk about with this subject, so we're going to spend probably the next 2 to 3 weeks just on path planning. So a very loose formulation of path planning looks something like this. We have some initial state that we can label as SO, and we have a goal state that we can label as SF. So that F stands for final, so our final state is our goal state. Our actions are motion commands. So in the AI classes, you probably talk about actions in a very discrete way. So you've got some problem like the in Queens problem, or maybe like traveling salesman problem, and your actions are some operations like, move queen from this spot to that spot, or go visit this node, and those are very discrete things. In robotics, our actions are going to be continuous because they're just going to be velocity and acceleration values that we send to the robot over time. So in order to change the robot state, we would say move move at 0.5 velocity in this direction. We could also say, well, what about 0.51 or 0.5111? So it really, the space of our actions, all the possible actions we can send to our robot, is going to be a big continuous space. So moving from the AI class to this class, you'll want to note that. In a lot of AI problems, your actions are very discrete. In robotics, your actions are continuous. And of course, we're going to have some transition model that defines how the robot moves. And really what that is what we went over last time in class. It's our control equations. So our input is going to be some kind of wheel speed and maybe our time, time to move at that speed. And then, if we have a car-like robot, maybe we'll give it a steering angle. And the output is going to be the change in the position, right? So like we have some state and that's our position. Our action is going to be some motion, and we want to, track how does our position change. That transition model is just that list of control equations. So eventually we end up with a function that represents our path. So our path is going to be a function p of t. I didn't put the actual function in here. I just put ... because there's no template for a path function. But the things that they all have in common are that our first state, p of t0, is going to be equal to our initial state. And our last state, p of tf, is going to be our goal state. And then for all t, no point on our path is going to intersect obstacles. So we have this notion, this set O, and that means it's the set of all states that intersect obstacles. So we can check p of t for any state in O, and we just want to check that, okay, we're not actually intersecting obstacles on our path. So your book talks about how this relates to control, and it's important to talk about because, again, control is part of motion planning. So really, if our path is some function, that just means that we have some function. We're trying to find an unknown function, which is essentially a control problem. And if we look at path planning with no obstacles, you can actually reduce that to an optimal control problem. So if we have the state S0 and we have another state SF, and we want to move from SO to SF, it's just a straight line. So if we have no constraints and we don't really have any obstacles or anything, the optimal path is just going to be a straight line. There's no faster way to get there. But of course, that's not possible in robotics. So the reason is that with every robot, we have some dynamic constraints. And by dynamic constraints, we just mean that the way that the robot can move is restricted in some way. So here I put a really simple car-like robot. You may recall that wheeled robots of any kind, so car-like robots or differential drive robots, they can only move in the direction of their wheels. So with this little car-like figure here, we've got this arrow up top, and that is supposed to represent the orientation of the robot. So when it's at XO, the only place that it can move, the only direction it can move in is up. So it can't physically move in a straight line from XO to XF. So we have to represent this as a control function. We have to consider this. And so the textbook that I assigned It gets pretty deep into control theory for mobile robots, and prior to this chapter, it covers a lot. I'm not going to go into that here in this lecture. I don't think that it's necessary to know, but I just wanted to list the basics here. So the basics are that we have some matrix here labeled as J, and that matrix is going to take in two things, X with an underbar and U with an underbar. And what we want to do is minimize that function. And so X bar is going to be equal to XY theta, so that's the XY position of the robot and the orientation of the robot. And then we have U bar, and so U bar is the control vector to send to the robot. So here we have U bar equals kappa in U. So U without the bar is just the speed, like the linear speed of the robot, and kappa is going to be the steering angle of the robot. So if you recall from the last lecture, those are the two inputs that you give to a car-like robot. You give it an overall speed, and you give it a steering angle, and based on that, we can figure out how it drives. So given its state, X bar and then its control U bar, you pass that into J, which is a matrix, and you want to minimize that set of equations, and that will eventually lead you to SF. I believe that should have been XF here, though. So just to kind of take this a little bit further, the third line here, I show D of X bar, so how X changes as S changes. Okay, yeah, that makes sense. So X is our configuration, XY theta, but S is just the XY values. So as the XY values change, the way that the configuration is changing is equal to this function down here on the bottom left, where we've got this 3x1 vector, cosine theta, sine theta, and kappa, and we're multiplying that by the overall speed. So if you recall from the equations that we had last time, this is the way that we're calculating the overall velocity, or the way that the position changes. X bar of S0 is equal to the initial configuration, so the initial XY theta, and then as we get to the final one, we have the final configuration here. Okay, so I just briefly wanted to touch on this. I don't think you need to know all of this. I certainly won't ask you to reproduce this set of equations, but it's important just to consider that when we have a robot, we have to consider the dynamics of the robot. We have to consider what the restrictions on its movement are. And when there are no obstacles, we can actually use these restrictions and still define an optimal control problem to move the robot. Where this breaks down, though, is when we do have obstacles. So what you see here is that we have some start S and we have a goal G on the right. And I've drawn 4 paths to get there, and they don't touch these obstacles that we have in the middle. And so what each one of these paths represents is a homotopic region. So when we talk about homotopic stuff, it's very, very important in robotics, but we're not going to talk about that too much here in this class. That's a bit more advanced topic for robotics that is left to the graduate level classes and to eventually the 4151 class for undergrads. But essentially, what I mean when I say homotopic path is that this path can be deformed to any other path in some region without hitting obstacles. And so what we have here are 4 homotopic regions. So each one of these paths is a homotopic path. So we've got the one at the very top that goes over both obstacles. We've got one at the bottom that goes underneath both the obstacles. And then we've got 2 that kind of crisscross. So they go over one and under the other. So if I tried to take the topmost path, the one that goes over both of them, and I wanted to deform that to the bottom one, the one that goes underneath both of them, I couldn't do it. It's impossible because there's no way to deform the top path without intersecting these 2 obstacles in the middle. And so these 4 paths here you actually can't deform any of them to form the other paths. So each one of these is like its own homotopic region. So think about all the paths that you could possibly form that go over both of the obstacles. So for all of those paths, I could change the path I have shown here, the one that goes over both obstacles, to anything in that set. But I can't change it to anything in the other sets. So the problem with this is that if we want to avoid the obstacles, then it's not really clear how we do it, right? So if another obstacle popped up and it intersected the path that we were currently on, then we've got new homotopic regions, and we don't actually know how to switch between them. So typically when you're thinking about control problems, the main technique to change functions, based on just control information, is that you deform the path towards a local solution based on gradient information. So what that means is that we have our path, so think about taking any one of these 4 paths, and we're trying to deform it based on local information. Local information is going to be the stuff that is near the path. So that would be like if we get close to the obstacle, then we would start considering that obstacle. And we would say, oh, we want to move away from that obstacle, or maybe we want to move closer to that obstacle. We would also consider the feedback from the robot. So is our robot moving in the correct way that we want it to move? And based on that stuff, so that actually stuff would be mostly the gradient information, and then the local solution is how we change our path based on the obstacle and feedback information. So in order to do this, there's 2 approaches. Either we treat the obstacles as constraints. So you might recall in the previous slide, we were talking about the dynamic constraints of the robot, and since we have to consider the dynamic constraints, we can't move on a straight line. So one option is to consider obstacles as constraints and somehow find a way to work obstacles into those control equations. Or you can try to account for obstacles in a cost function and say, okay, well, I'm trying to minimize this function. So the obstacles aren't necessarily restricting how I'm trying to move, but I still want to find a way that minimizes this cost function, minimizes my how close I get to the obstacles. So what that means, there's 3 problems with this. So in order to minimize the path, so if we're trying to optimize our motion to get from S to G as fast as possible, is that we have to deform our path to get really close to obstacles. And just in general, that is bad. That's bad in robotics, because in robotics we want to avoid obstacles. We want to do the opposite of get close to them. We want to get far away from them. So what you end up doing is making your robot come really close to obstacles and then accidentally just running into them. And generally if we intersect with the obstacles, then we have failed our path planning. So we would not consider that a successful path. Another issue is that it's not clear how to switch between homotopic paths. So I briefly mentioned we can't really deform one of these into the other paths. So if we need to switch, we don't really know how to do that. So if we take the topmost path here, the one that goes over both obstacles, that's a fairly simple curve. That's going to be some kind of x squared function, right? A very, very wide parabola. And the ones that go above and underneath the obstacles, those are not parabolas. Those are kind of summing up 2 different parabolas, or you could also think of it as a 3rd order function here. So those can be 2 totally different functions, and you can't just instantaneously switch from a function that's 2nd order to a function that's 3rd order very easily. So we have this very mathematical issue with trying to switch between the 2 homotopic regions. And then also you get subject to local minima. So local minima means that somewhere in this environment you may find a space where if you are almost surrounded by obstacles, when you try to deform your path, you just can't escape that region. And so that's something that actually comes into play a lot in robotics. So basically what we're trying to show here is that while we can use optimal control to move a robot when there are no obstacles, and that works pretty well, when there are obstacles, this really doesn't work, and it doesn't really work very well. So the solution to this is that we discretize the space, and then we reduce the problem to a graph search problem. So here we have this graph that goes around these obstacles and leads us from S to G, and the nodes are going to be the states of the robot. So it can be X, Y, it could also be X, Y, theta, so we could consider the orientation in here. We could also consider the dynamic information. So we could have X, Y, theta, and then V, and V is like the linear speed of the robot, and then omega, this W-looking symbol, omega would be the angular velocity of the robot. How you represent your nodes is largely up to you, the person designing the algorithm. So there's no set in stone way of doing it. Then the edges are the control. So if I want to move from one state to another state, that might be a straight line, and we might be able to get there very easily. So in those cases, we can use just optimal control to move there. So our nodes represent the states that we want our robot to reach, the states that we want our robot to be in, and the edges represent how we move between those states. And essentially, this leads us back to our state transition function, where our state can be x of k, so k is the time, and then if we have some control vector u, we have our state transition function. So if we're at xk and we apply u, that gives us to xk plus 1. And so for all these x's here, you can think of them as nodes on the graph. So there are many different ways to discretize a space. So the one we just looked at was an embedded graph. So we just choose some states to be the nodes. We define the control that transitions between those nodes, and we can just do that allows us to move from the start to the goal. A grid is another way to discretize the space. So a grid is dividing the space into equal size cells, and each cell is a node, and each cell has edges to all of its neighbors. So it's very likely you all have worked with grids before, and those are something that are pretty intuitive. A lattice is similar to a grid, but its edges can extend past its neighbors. So lattice is mostly concerned with the symmetry of your edges. So if I have nodes all around me, I should have edges to all of them. And a grid is actually a type of lattice. There's also something called a Voronoi graph. So those are graphs where each point has equal distance between the two closest obstacles. So at each point on the graph, you're actually kind of traveling in the middle of all the obstacles. There are many other types of ways to discretize a space. I'm not going to talk about all of them here. We will probably talk about a handful in the class, but just know that these are kind of the most basic ones, and there are more that exist. And once you have some way to make your space discrete, and you can do graph search, you just employ graph search algorithms. So breadth first search, depth first search, A-star, things like this, and that moves you from S to G. And then once you have your path, you can just use some basic control to move on the edges. And if your environment doesn't move, then you're good to go. So I'm not including stuff about graph search algorithms here. If you've taken AI, then you're probably familiar with these. If you are currently taking AI, you're probably talking about this stuff right now or about to soon. So what I'm going to do is post information on Canvas about search algorithms. So I'm going to post a video, maybe at least one video about search algorithms, and that's just something I gave my AI class. So it'll be talking about search algorithms, but not really in the context of robotics. But it should still be enough for you to understand what we're talking about. So there are lots of further issues in path planning. I put some of the most fundamental questions here. So what if our environment is too large, or if it's high dimensional? So if it's too large, then it might take too long to search through. So we have to find a different way to make it discrete so that our discretization is more efficient. What if our environment is dynamic? So what if, our obstacles are moving around? In that case, it becomes hard to discretize the space, because if your obstacles move and they intersect one of your edges, now your graph doesn't really represent your space very well. So with this topic, we start talking about how to model the obstacles, how to do obstacle avoidance, or how to plan really fast. What if your environment is unknown? So what if you don't actually know where the obstacles are in the environment? If that's the case, you have to rely on sensor feedback to kind of navigate the environment. And what if your robot is not easily controlled? So you can consider a car-like robot here. With the car-like robot, you're pretty much going to have to encode the dynamic information into the state space. So at each one of your nodes, it's going to have to be like X, Y, and then theta, and maybe the steering angle as well. Because it's just so hard to control those robots, you can't really rely on easy ways to satisfy the control equations. So we're not going to talk about all of these in this class. We will probably talk about the first two, so having large environments and having dynamic environments. First, we're going to talk about large environments. And then for dynamic environments, that will probably be something that if we do talk about it, it'll be towards the end of the semester. So just to recap, motion planning is the combination of both path planning and control. And path planning is really helpful because it helps us deal with obstacles in the environment. If we had no obstacles, we could just use control. But because there are obstacles, we have to have some other way to deal with it, and that's where path planning comes in. The most basic approach to path planning is to just discretize our space and then do graph search. And again, there are many different types of ways to make your space discrete, and we'll talk about some of those going forward. And there are lots of questions and issues to consider in path planning, like dynamic environments, unknown environments, things like that. So what we've shown here is kind of the most basic version, and as time goes on, we'll get into more and more complicated path planning problems. Okay, so that's all for now.